Cis and trans isomer. The cis and trans isomer can be distinguished by following method. So how we can identify between the cis and trans isomer, which is very quite confusing. The spatial arrangement of donor atom of a ligands, then the position of a methyl group which is bonded to secondary carbon atom and that is bonded to the donor atoms. So all this type of specific particular points which make the difference between cis and trans is very too much to have big information about it. Then the cis form, which is also in the form of facial, and trans form, which is in the form of meridonian. The difference between facial and the meridional. So how we can identify cis and trans form with the help of some instruments. So there are some methods. Dipole moment measurements. The trans isomer has dipole moment equal to 0 because the dipole moment of one ml bond is cancelled by the dipole moment of other ml bond lying on the opposite side. So why the trans isomers show 0 dipole moment? Because the metal and ligand bonds which is lying on the opposite to each other cancel each other dipole moment. That means because of the repulsion between the ligand cause the one metal ligand bond to cancel the dipole moment of other metal ligand bonds. That's why trans isomers dipole moment is 0. In cis form, the dipole moment of Ml bond, which are cis to one another, contribute in the same direction, resulting in some value of dipole moment. But in cis isomer, the ligands are adjacent to each other, next to each other. So the ligands which is adjacent to each others, they are shifting their dipole moment value towards same direction, towards one direction. So there is some enhancement of dipole moment. The value of dipole moment is enhanced because it is going in the same direction. And why it is going in the same direction? Because both the ligand are adjacent to each other, next to each other, close to each other, and that's why cis form show the dipole moment, but trans form isomer doesn't show any dipole moment. The dipole moment of trans isomer is 0 only. Infrared spectroscopy. In order for a molecule to absorb infrared radiation to cause vibration, there must be change in the dipole moment of a molecule as it vibrates. So how we can use the infrared spectroscopy to study about this kind of cis and trans isomer difference? So for that, the molecule should absorb the infrared radiation. So some kind of vibration will be there. And what will happen when the molecule will vibrate? There will be some changes in the dipole moment. In case of trans complex such as PTNS3 2Cl2 and CONS3 4Cl2, the Cl metal Cl symmetric stretching causes no change in the dipole moment of the molecule. But if trans form complex will be there in presence of infrared radiation, the Cl metal Cl, the symmetric stretching, will not make any changes in the dipole moment of trans isomer. We know that trans isomer dipole moment is 0, and in presence of infrared radiation, the Cl metal Cl symmetric stretching will not make also any changes in the dipole moment. Therefore, these two compounds are IR inactive and no bands corresponding to the symmetric stretching vibration is observed in the infrared spectrum. So these two trans isomer complex will not show any changes in the IR. Their symmetric stretching vibrations will not show any bands, and that's why both the trans isomer complex are IR inactive. These are inactive because symmetric stretching vibrations will not show any band in the IR spectrums. In case of cis form, the complex, both the symmetric and asymmetric stretching vibration of Cl metal Cl bond cause appreciable changes in dipole moment. But on the other hand, if we will keep a cis isomer complex in presence of IR radiations, the symmetric and asymmetric stretching vibration, there's two type of stretching vibration, which is symmetric and asymmetric, of what of Cl metal Cl bond will make any changes in the dipole moment. So this cis isomer complex we will keep in presence of infrared radiation. Then both type of stretching vibration, that is symmetric and unsymmetric, will make any changes in the dipole moments. So the cis isomer will show IR active, but trans isomer will not show any symmetric stretching vibration. So there will be no changes in the dipole moment. The dipole moment will be remain 0 in the trans isomer. So trans isomer is IR inactive. That means trans isomer doesn't show any IR active, but cis isomer show IR active, because the symmetrical stretching and unsymmetrical stretching make changes in the dipole moment, and that's why the cis isomer will show IR active. Thus, this mode of vibration of cis complex are IR active. There are number of bands in the infrared radiation. So cis complex show IR active, and when we will study its infrared spectrum, then number of band will be there, which give the proof that cis isomer is a IR active. So here, this is the transform Cl. Okay, so this both the Cl will cancel each other dipole moment, and the Cl symmetric stretching vibrations will not make any changes in the dipole moment. So it will be dipole moment will be 0, and it will be IR inactive. That means it is not IR active. On the other hand, the cis form Cls, they have their dipole moment, and both their dipole moment is going towards the same direction. So the dipole moment will be enhanced. That means there is some changes in the dipole moment in the cis form, and on the other hand, when it will come in contact of IR radiations, the symmetric and symmetric will make a changes in their dipole moment. So cis form is IR active and transform is IR inactive. Next is chemical method, Greenberg method. So what is this method? When a chelating ligand such as NH2CH2COH or COH oxalic acid, this is one glycine, NH2CH2CH2 NH2 ethylene diamine. When this kind of chelating ligand react with cis and trans isomer, the cis isomer form chelated complex or chelate. Cis isomer will form chelate complex. Trans isomer form non-chelated complex. So the cis isomer with this bidentate chelating ligand will form chelated complex, but the trans isomer will not form trans isomer will form non-chelated complex. Reaction, for example, cis and trans PTNSC2Cl2 with CO2O42- and NH2CH2CO- are shown in 2.38. So here this is cis form, cisplatin react with oxalic acid. So the donor atom oxygen oxalic acid is forming chelating ligand, chelated complex. Now on the other hand, glycine is there. So the two different donor atom of glycine make a bond with the platinum, it forms chelated complex. But on the other hand, this is the transplatin oxalic acids, where the two donor atoms of oxalic acid, okay, they will form non-chelated complex. That means it will not show any ring complex. In cis form, when the cis form was reacting with the bidentate ligand, it was showing a kind of cyclic structure, okay, whether the donor atom is same or not, but still the cis form was showing the cyclic structures. But in trans isomer, two oxalic acids are there, but still they are not showing any cyclic complex, any cyclic structure. So that's why trans isomer in contact with symmetric bidentate ligand or unsymmetric bidentate ligand will form non-chelated complex. That means it will not show the cyclic structures. So here with the oxalic acid it shows cyclic structure, and with glycine also is showing non-chelated complex, that means non-cyclic structure. So quantitatively it is observed that for 1 mole of cis isomer, 1 of NH2CH2COH or oxalic is used. For the cis isomer, 1 molecule or 1 mole of glycine or 1 mole of oxalic acid is used. But on the other hand, for the trans isomer, 2 moles of or 2 molecules of oxalic acid or 2 moles of or 2 molecules of glycine is used. Whereas for 1 mole of trans isomer, 2 moles of either NH2COH and COH is used. For 1 mole of trans isomer, 2 moles of glycine and 2 moles of oxalic acid is used. But for the 1 mole of cis isomer, only 1 moles of glycine and 1 mole of oxalic acid is used. Cis isomer form chelate with chelating ligand because the two donor atom coordinate on the adjacent position, resulting in less strain. Why this cis form make a chelating ligand or make a chelate or cyclic structure with a chelating ligand? Because the two donor atoms or bidentate ligand coordinate with the center metal on adjacent position or next to each other, and that's why when they are next to each other, adjacent to each other, there is a less strain. But in case of trans isomer, the two donor atom chelating cannot coordinate at trans position because of large strain. But the trans isomers is unable to make a chelate or the cyclic structure with a chelating ligand because these two donor atom of chelating ligands on the opposite position or trans positions form a large strain, and that makes unstable complex. That's why trans isomer will not form chelate with the chelating ligand. This large strain causes the instability of the chelated complex. So the cis will form chelate with the chelating ligand, will form cyclic structure with the chelating ligand, but trans will not form any cyclic or chelate structure with chelating ligand because of the large strains. Optical isomer or mirror image isomers.